All right, everybody, here we are, and we are about to get into our second slideshow about enzyme inhibition and enzyme kinetics. We're going to be getting into inhibition today, or with this lecture. So with that said, let's go ahead and get cracking. So one of the more important things for you to think back on is the two models that we looked at, or the two graphs that we looked at. The first plot was the Michaelis-Menten plot, and then the next plot was a double reciprocal plot. So our labels for our y-axis for the Michaelis-Menten plot were velocity versus substrate concentration, whereas our double reciprocal plot was 1 over velocity versus 1 over substrate concentration. So if you know that this, you collect data to plot that graph, then you basically translate that onto this graph. That's going to be if you understand that, that's a very good starting point. So the first thing that we need to talk about with respect to kinetic versus chemical mechanism is a kinetic mechanism is the order of substrate addition and product release in an enzyme catalyzed reaction. We previously talked about chemical mechanisms, so pushing electrons around. A chemical mechanism is the chemical pathway of conversion from substrate to product, including the structures of intermediates. Both are needed to understand an enzyme's mechanism. Kinetic mechanism can disprove a chemical mechanism, and that's one thing that's very important to recognize. Now, most of the time, when we talk about an enzyme, we've talked about a couple of enzymes that fall into this category that are bi-substrate, meaning they have multiple substrates, or at least two substrates. Now, the Michaelis-Menten model of enzyme kinetics was derived really for only one single substrate, but the majority of enzyme reactions have multiple substrates and products. One example that we've looked at quite often is the enzyme hexokinase, which utilizes ATP and glucose. And by utilizing ATP and glucose, it's utilizing two substrates. Now, a bisubstrate reaction accounts for about 60% of the known enzymatic reactions. Examples, a large proportion of bisubstrate reactions are transferase reactions or oxidoreductases or oxidation reduction reactions. So transferases and oxidation reduction reactions. So here's a couple of examples of a transferase reaction as well as an oxidation reduction reaction. Now, how do we actually use a bisubstrate reaction, or how do we make a bisubstrate reaction look like a uni-substrate reaction? So if we're talking generally about a bisubstrate reaction, how do we get it to match this sort of graph where we're plotting the concentration of one substrate? Well, when we do that, what we're wanting to do is basically, or the way that we can do that is we want to determine the rate at various substrate concentrations from when the substrate concentration is lower than the Km to the substrate concentration is greater than the Km. Now, to make a bisubstrate reaction perform like a uni-substrate reaction, we keep the concentration of one substrate at saturation while studying the other substrate. So we'll basically provide an excess or the saturating amount of substrate B, and then we'll vary substrate A. And then we do the opposite. Saturate with A and then vary B. Now, what we can use this for is we can learn about the order of substrate addition and product release in most enzyme reactions. And they're going to follow two models. Oh, I apologize. They're either going to be a sequential reaction in which all substrates must bind to the enzyme before the reaction occurs and products are released. These are ordered sequential and random sequential, or they are a ping pong reaction where one or more products are released. A product is released Before all substrates have been added, an alternate stable enzyme form F is produced in the half reaction. So first we're going to look at a sequential reaction. So we have sequential versus ping pong. Sequential reaction is all substrates must bind before the reaction occurs and products are released. So here's an example of that. Below the line, we have written E for our enzyme. Then the first thing that's introduced is A, our first substrate. And we form this EA complex. So that's the enzyme and substrate number one. Then we have our second substrate labeled as B come into play. And B comes in and binds to that EA complex, resulting in EAB, which EAB is going to result in the formation of our two products, P and Q respectively. And we so briefly have this EPQ complex. That EPQ complex is going to release P, leaving behind EQ, and then Q is going to be released, leaving behind E. Now, it's in that EAB, EPQ where the chemistry and the reaction is going to take place. This is considered an ordered sequential reaction. And what this in this model shows is that A must bind to E before B can bind, because B basically has no ability to bind free enzyme. Instead, B is going to bind to the enzyme EA, or the enzyme and substrate 1 complex, where we get EAB. Now, a random sequential model is, well, different from an ordered sequential model. So rather than there's a necessity for one thing to bind and then the next, and then the next, instead, with a random sequential reaction, it doesn't have to be A binding before B or B binding before A. You just have to have one of them bind and then the other one will bind. And for that model, we have this display on the lower right-hand corner of the screen, where basically our enzyme can go in two different directions. Either it can bind A, resulting in EA, and then bind B, and then result in EAB. Or the free E can bind B, or E, forming EB, and then A can bind, and you get some similar EAB variation. And then on the back end, the products or the two different products, P and Q, can be released in different time frames. So that's what's important to recognize about these two models. Either there is a required order or there is a required kind of randomness. Now, the ping pong model, I think, is fairly interesting because what it shows is it has two instances where the so-called chemistry is going to take place. Now, what's going to happen is a free enzyme is going to bind substrate 1, call it A. It's going to form EA. The reaction is going to take place. A is going to be converted into P. E is going to be converted into F. So E is fundamentally different than it previously was, and is now in this new form F. So once we have F, we've got B that can bind to F, forming the FB complex. Now the thing is, what this is saying is that B, this substrate, has like no affinity for E. It only wants to bind F, the modified form of B. So whenever we have that take place, we have FB, then EQ, where our product Q is generated, and our free enzyme E is ultimately released. So for these reactions, we have two instances where the so-called chemistry is taking place. Now, almost always the modified form has, or the modified version of the protein F has a covalent bond formed to the substrate. Now, sequential and ping pong models can be distinguished on the basis of their likely word plots or double reciprocal plots. Our initial velocity plots, when we're looking at sequential reactions, exhibit an intersecting pattern of lines. And order and random substrate additions cannot be distinguished in this type of plot. So we're going to see something like this, where our intersection is in this, I believe this is quadrant 1 or 2. I can't remember which quadrant this is on a plane, but essentially we have this intersection there. Now, a ping pong reaction shows parallel or non-intersecting lines, where we have these very minor separations between each one of our product lines there. Now, enzyme inhibition. Many substances bind to enzymes and decrease the velocity of the enzyme catalyzed reaction. These are known as inhibitors. Enzyme inhibitors are important for a variety of reasons. Now, they can be used to gain information about the shape of the enzyme active site and the amino acid residues in that active site. They can be used to gain information about the chemical mechanism, the order of substrate binding or product release, and formation of intermediates. They can be used to gain information about the regulation or control of the metabolic pathway. And finally, they can be used and be very important in drug design. When it comes to enzyme inhibition, there are inhibitors that are reversible. These are substances that bind to an enzyme to inhibit, but they cannot be released. So that means you could imagine that the enzyme has a very high affinity for that substrate, and it's probably there's probably a covalent bond as opposed to a non-covalent bond like an ionic or a hydrogen bond. So, or sorry, it can be released. So, yeah, reversible. We've got a non-covalent bond. Generally, there are going to be two types. There are dead end and product. Irreversible inhibitors, on the other hand, substances that cause inhibition that cannot be reversed. And these are usually going to involve a covalent bond to or on the enzyme. This is fairly dense, but there's a handful of slides that I'm going to put a star on that are the highest value slides. So inhibition patterns. Inhibitors act in a variety of mechanisms. An inhibitor may bind at the same site as one of the substances, or of the substrates. These inhibitors structurally resemble the substrate. An inhibitor may bind at an alternative site or an alternate site, affecting catalytic activity without affecting substrate binding. Now, many inhibitors are going to do this. So the substrate will bind, but the inhibitor will also bind. Now, the most common types are competitive, and these are the three things that we're going to focus in on. And these are the things that I really want you to know these graphs very well. Competitive inhibitors, mixed or non-competitive and uncompetitive. So those terms mixed or non-competitive and competitive, they may seem a little bit redundant, but I'm sure you're there or not. They're affecting an enzyme, or they affect enzymes in different ways. So inhibition patterns. A competitive inhibitor competes with a substrate for the enzyme, specifically the substrate binding site. So when we talk about these different patterns, these different types of inhibitors, the first one is a competitive inhibitor. And I think that's easiest to understand this because it's one, the name competitor or competition is something that you've maybe pulled from your somewhat everyday language. This competes with the substrate for the enzyme, specifically the substrate binding site. So imagine that you have an enzyme and a substrate, so that ES complex is kind of the desired goal. Well, a competitive inhibitor more or less blocks that out and goes to the enzyme in place of that substrate. And whenever I say blocks it out, I mean it goes to the binding site on the enzyme that the substrate otherwise would. The inhibitor and the substrate here, they're not going to necessarily interact, or they're not going to interact with one another. That's not how the blocking is going to happen, but rather this inhibitor goes to the enzyme, binds to it, substrate can't bind. Okay, now what we see here, and what I was describing there, is basically, if you look at this path right here, this is kind of our desired outcome. The enzyme plus the substrate interact to form the ES complex. The ES complex breaks down into the product and the free enzyme. Okay, now that is the case in the absence of an inhibitor. Now, in the presence of an inhibitor, we have the enzyme, the substrate, and the inhibitor. And lo and behold, the inhibitor binds to the enzyme, form an EI complex. What remains is, well, there's free substrate in that solution. All things told, though, there is no reaction, no product's going to be generated in that way. Now, with that in mind, that's kind of a simplistic way of thinking about it, because these two lines right here indicate that we have formation of the EI complex and then breakdown of the EI complex, formation, breakdown, formation, breakdown, formation, breakdown. And at some point, that inhibitor will no longer be associated with the enzyme, in which case the substrate could bind and there you could generate your product. But for the purposes of this discussion, I want you to think about this as the inhibitor is able to bind to the enzyme, preventing the substrate from binding to the enzyme, therefore preventing the formation of our product. Another type of inhibitor is an uncompetitive inhibitor. Let me go ahead and draw these lines to kind of break things off a little bit. There we go. An uncompetitive inhibitor binds to the enzyme substrate complex. So in this case, we have that ES complex that results from our enzyme and our substrate. That ES complex will interact with our free inhibitor and form our ESI, our enzyme substrate inhibitor complex. That enzyme substrate inhibitor complex is going to, well, prevent any sort of product from being generated. So in this uncompetitive inhibition model, we can, should the inhibitor bind, prevent the formation of our product. Now, our last model is a little bit tricky. This is a mixed inhibitor. Now I'm going to draw a line. There we go. Well, this is tricky because the inhibitor here is going to be capable of binding to the free inhibitor, free enzyme, but it's also capable of binding to the enzyme substrate complex, in which case it basically has two ways to prevent the reaction from taking place, to prevent our product from being generated. Now, how do we distinguish between these different types? Well, what we're going to do, or what we would do, is generate what's called an inhibition plot. This is similar to an initial velocity plot, but we use an inhibitor instead of a second substrate. So what we can get from this is some idea of what's happening and what's binding, and therefore what type of inhibition is present. Now, Ki is the equilibrium constant of the inhibitor binding to the enzyme. Now, Ki, I want you to think about as something that can absolutely be determined, but we're not going to, or I'm not going to expect that of you. Ki, what you can do with it is determine basically the affinity that the enzyme has for that inhibitor based on a couple of different plots that you would generate. So when now kind of changing gears back to competitive inhibition or competitive inhibitor, we have an example of a competitive inhibitor here is the molecule succinate. Succinate is the natural substrate for the enzyme succinate dehydrogenase. This enzyme undergoes a oxidation reduction reaction to produce fumarate. Now, malonate is a molecule that if you look at succinate, succinate is carboxylic acid on the top and on the bottom. Malonate is a carboxylic acid top and the bottom. What brings them to, or what brings them together for succinate is 1, 2 CH2s, and for malonate it's 1 CH2. So you can kind of look at succinate and malate and say they're very similar, but one's a little bit taller than the other. Well, malonate is an inhibitor, a competitive inhibitor for succinate dehydrogenase. It resembles the natural substrate, so it can bind into that substrate binding site. Competitive inhibition, well, here's that model for binding between the enzyme and the inhibitor. A competitive inhibitor ultimately is going to reduce the amount of free enzyme available, for substrate binding, thus increasing the KM for the substrate. So what does this mean? It increases the KM for the substrate. If the KM goes up, then the affinity for the substrate goes down, okay? So what this effectively means is that if you give this enzyme and inhibitor mixture more and more of the substrate, your substrate can outcompete the inhibitor. The effect of a competitive inhibitor can be overcome with a high concentration of the substrate. So I guess you could kind of look at this as, and what I want you to kind of be keeping track of at home is we've got Vmax, Km. Well, if the Vmax, and these are things like we want to ask, do they change? With a competitive inhibitor, there's no change. The Km is going to go up. So substrate affinity goes down. Now, here is a set of Michaelis-Menten graphs and a double reciprocal or a Lineweaver-Burke plot. Now, one thing that I'd like to draw your attention to for this Michaelis-Menten plot, so we've got our maximum velocity. We have also our Vmax divided by 2, where we can calculate our Km. Okay. Now, what I'd like you to look at with these lines is this, let's say this olive colored one, that's basically going to go on to infinity. This curve is going to continue going up and will ultimately reach the exact same as our previous one, as our no inhibitor present. And then this last one, it's going to continue rising up, rise, and then it will ultimately hitch up with that first line. So our Vmax does not change with a competitive inhibitor, but our Km does. As you can see, our Km here, here, and here. Our Km goes up with a competitive inhibitor. What does that look like on a Lineweaver-Burke plot? Well, that means that the slope of your line, let's see, no inhibitor, but then it gets more steep and even more steep. Your slope increases. So competitive inhibition, there's a couple of ways to calculate the Ki. You can calculate the Km with and without the inhibitor present, or you can calculate the slope with and without the inhibitor present. Now, like I said, I'm not going to ask you to be able to calculate your Ki's. However, this is your way to do it, or these are two ways that it can be done. And it just tells you the affinity, oh boy, the affinity that your enzyme has for that inhibitor. Now, next up is uncompetitive inhibitor. An uncompetitive inhibitor or uncompetitive inhibition, it binds to the enzyme substrate complex, but not the free enzyme. So this ES, when we're just about to generate the product, the inhibitor swoops in and says, not so fast. So what this leads to is your Vmax goes down, your Km goes down. Now, the interesting play about the Km going down is that basically argues that it makes your enzyme have a little bit more affinity for the substrate. So that's one thing that's worth noting. The reason for that is every time that you're putting that free enzyme, every round where there's free enzyme, some of it's going to make this ES complex and make this ESI complex and basically get stuck in that channel. But nevertheless, your enzyme's affinity for the substrate, the affinity is going to go up because the Km is going down. But ultimately, the rate of the reaction is going down. Now, with that said, when we talked about a competitive inhibitor, if we provided it with more and more substrate, well, then we're going to be able to outcompete that inhibitor. But here, we want the ES complex, so the substrate's provided. And the substrate binding to our enzyme is not impacted at all, really, by the presence of that uncompetitive inhibitor. Now, the effect of an uncompetitive inhibitor cannot be overcome by excessive concentrations of the substrate, which is what I mentioned just a moment ago. Now, an uncompetitive inhibitor, since the Vmax and the Km, these are both going down, what does that mean for our graphs? Well, one thing is the slope of these graphs isn't changing because both our Km and our Vmax are both going down. So our slope remains unchanged. The Km goes down because our affinity for our substrate has effectively gone up. Now, our maximum velocity has also gone down. So another way that you could calculate, or a way that you could calculate your Ki is you could determine the y-intercept with and without the inhibitor present. You can determine the x-intercept with and without the inhibitor present. Now, a mixed and a non-competitive model. This is a little bit tricky because this is a combination of different kind of models and different displays. So this is the type of inhibition where an inhibitor can bind to both the free enzyme and the enzyme substrate complex. To put that into a graph is a little bit tricky. The inhibitor can bind to both the free enzyme and the enzyme substrate complex displayed. The affinity of the inhibitor to the two complexes might be different. If binding of an inhibitor changes the affinity for the substrate, the Km will be changed, and this is referred to as mixed inhibition. So basically, you could kind of think about this I right here. It is capable of binding the free enzyme. It is also capable of binding the enzyme substrate complex. But this is getting at, well, what does it do in practice? This is kind of like, you know, I designed this thing for you to love, like, or I baked you this cake and it's a chocolate cake because I know that you like chocolate. And then you hand it to the person and you're expecting some sort of return, some sort of response. It's possible that they're going to bite into it and say, well, I like Snickers bars. So I like chocolate on Snickers bars. I don't like chocolate cake. Similar here, we're saying, I'm expecting this to happen because it's capable of binding both things. I'm expecting it to bind to both of those things. But this says if binding of the inhibitor changes the affinity, not so it doesn't drive it down, doesn't drive it up. This is changes the affinity for the substrate. The Km will be changed, and this is called mixed inhibition. So if it impacts the Km, it is mixed inhibition. Now, if only Vmax changes, then this is called a non-competitive inhibitor. So that's why this kind of has displays of competitive and uncompetitive and what they look like. Now, here's some of our graphs. So if only Vmax is affected, this is a non-competitive inhibitor. But if Km will be changed, it's a mixed inhibitor. Here are some of the different graphs where you can kind of explore these different models. Now, the result will be a decrease in Vmax for mixed inhibition and an increase or a decrease in Km. So Vmax goes down, Km could go up or down. The effect of a non-competitive inhibitor can only be partially overcome by high concentrations of the substrate. Okay. So mixed inhibition, there are a couple of ways that this can get calculated. You can determine the y-intercept with and without the inhibitor present. You can calculate the slope without inhibitor present. And there's what you get. Now, this graph down here, you're being asked, is this mixed or non-competitive? Well, the x-intercept of mixed inhibitors is kind of complicated. But when the Ki is the slope and Kiy, or is equal to the Kiy intercept, or in other words, the inhibitor has equal affinity for both E and ES, then the x-intercept converges to one point on the axis. This is known as purely non-competitive inhibition. So essentially, if the inhibitor has equal affinity for both E and ES, it is purely non-competitive inhibition. So to go back to the Oreo cookie lyase experiment, here what we have is a series of trials where, well, we introduced an inhibitor, fig Newtons. We put 1 fig Newton down per desk. And here's the graph that came from it. Okay, so just sort of speculating that our Vmax is right about here. Okay. Now, Vmax over 2, 17, it's going to be 8.5. Right about there, a little bit under 1. Now, for our other type of inhibitor, our Km went up. So Km and so that's one piece of data that we can get from this. What we can also do is take that same data right here and get the reciprocal of these values. That's where we can come up with this plot right here. Now, you can see that these data can merge together at this point right here. If you can imagine the slope of this blue line, we're going to end up with a slope like right there, whereas our yellow line is our Km. So, oopsies, we have Km, here we go, that has changed. We have a Vmax that looks like it has not changed. So what I want you to know about these, or from this, the important points are, I want you to know what a mixed inhibitor graph looks like. I want you to know about these models right here. What is forming, what is being added. Those are things that I want you all to know about. I think they will be very helpful for y'all so that you can be successful in the exam. But at any rate, I hope this is helpful and I hope you have a good one.